perspective, will give us a very valuable perspective on this. So please give a warm welcome to Donald. Thank you. And
thank you, Piotr. I'm getting over a little bit of a cold, so my speaking voice won't be terribly good. But I wanted to start, and hopefully we will get a clear signal. Okay. I want to just start with, Pavel gave me a little help on this, so he's not responsible for what it sounds like, though. So, Dzień dobry państwu. Cieszę się, że jestem w Polsce. Przepraszam, że nie potrafię mówić po polsku. Okay. So Polish is not a language that I've invested any time in, so that's my excuse. Okay, so what I want to talk about is making money with variability. I think there are some, I tend to see some perennially bad ways of thinking about variability in the product development world. Some of them date back to the waterfall method of product development, but I want to try to give you a little more advanced way of thinking about variability, which leads you to different conclusions about how you manage variability. So what I'll do is I'll start with this statement, which I think captures the way a lot of people feel about variability, that the best way to manage economically unfavorable outcomes, and most of you know I focus on the economics of these things, not the philosophy, is to reduce their likelihood. So do any, and certainly methodologies like Six Sigma focused on reducing the incidence of bad things happening. So we've got a long history of zero defects, Six Sigma, and things. Do all of you feel this is a true statement, that that is really the best way to deal with the problem of variability? And if you do, I'm going to try to give you a different way of looking at it. Okay, so the things I'm going to talk about today is I'm going to talk about the concept of anti-fragility. That's there's a guy named Nassim Taleb. Have any of you read the book Anti-Fragile? Yeah, a number of hands go up. Really useful perspective on something. He doesn't take it all the way to application, but it's a very different way of looking at the world. Then I want to talk about the deterministic legacy that we come from. We tend to be, most of our traditional models for managing product development was based on a belief in determinism, that if we try hard enough, we can end up predicting things accurately. I'm going to take a look at that a slightly different way, because a really nice way of looking at things stochastically as opposed to deterministically is what we do in financial theory with option pricing models. So I'm going to walk you through how an option pricing model works and things, and how it ends up processing the behavior of a random variable and estimating the economic impact of a random variable. And then what I'm going to do is I'm going to, one of the important things in those models is payoff asymmetries, and I'm going to start focusing you on the importance of payoff asymmetries as ways of making variability, making money. And then I'll finally talk a little bit about this notion of, is a good program really a program that meets its performance objectives, its schedule, and its budget? And maybe present an alternative view on that. Okay, so Nassim Taleb, really sharp guy, comes out of the financial world. He coined the term black swan before we had the big financial crisis. That sort of put him on the map. One of his newest book right now, I don't think the latest one has come out yet, but his newest book, Anti-Fragile, he coins this term anti-fragility. And what Taleb means by anti-fragile, he says, the way, I'll save you reading a lot of the book. He says, the way we think about fragility is a fragile system is one that will end up producing worse outcomes when it is subjected to a disruption. And so performance goes down when we end up disrupting a fragile system. And a robust system is this sort of blue line up here, is robustness was always our solution to fragility. We just give the system so much inertia that no matter what insult you give to the system, it will persist and continue to achieve its high level of performance. And Taleb says, there's another way to look at it, is why don't we think of the opposite of fragility as being anti-fragility? Is why don't we create systems that get better outcomes in the presence of variability instead of worse outcomes or no change in the outcome? He says, that's what we ought to create systems that performance goes up when we subject it to variability. Now, why would he ask that question? Because we have lots of, in the financial world, we have financial instruments that achieve just that thing. When variability goes up, they end up making more money. The problem with this idea of anti-fragility is you say, wow, that sounds really good. Where do I find this stuff called anti-fragility? Do I go to the supermarket and look on the shelf next to anti-gravity and I'll find anti-fragility? Nassim doesn't really explain where you find it or how you create it. And I'm going to give you some ideas on that in a product development context. So where we start from because anti-fragility is a concept that we apply to random variables when we have a stochastic view of the world. We're really starting very much in product development with a very deterministic view of the world. That is what led to the waterfall model. So we tend to have a lot of method. The method we use to manage is always a reflection of an underlying worldview. How do I view the world as being predictable? Do I view the world as being unpredictable? The deterministic worldview ends up being, if I try hard enough, I can make accurate predictions. That it's not that it's fundamentally impossible to predict, it's just I have to invest a lot of effort to get really good methodologies to get good prediction. I would say the stochastic view of the world assumes that we will never be able to cost effectively produce accurate predictions. So we'll have to use other methodologies. And Agile is really probably the preeminent stochastic-based system in contrast to waterfall, because it really believes in adaptation. And I'll get into that a little later. Now, the difference in mental set is when you are dealing with random variables, and I'll explain what I mean by a random variable a little more rigorously. It's a very different world than when you are dealing with a non-random variable. So a non-random variable might be, I fill a jar with a bunch of beans, and then I ask you, estimate the number of beans in the jar. The number of beans in the jar is a fixed finite value. And depending on how good you can estimate, you could end up getting the correct answer. Now, let me illustrate the, where you end up with this deterministic view, you start believing that all facts are known and stable, that you can do excellent forecasts, that nothing is going to change during your development process. And then since you know you can build accurate plans with accurate facts, you can then subdivide that into phases and have the phases check in along the way in the process. But it's all premised on the idea that the quality of our information is good enough to end up making that investment in big upfront planning highly accurate. And occasionally you may find a problem that falls in that domain. And the only use of feedback loops in this deterministic model is to return to plan, right? The plan is accepted as being 100% accurate. You would never want to aim for a different target. Now, this leads to a whole set of methodologies: large batch size, long cycle time, delayed feedback, has an effect on quality, has an effect on cost. I personally, not being primarily a software person, I personally do not believe that the waterfall model is evil. I believe that it's a planning-centric approach that is suited for a deterministic world. So if I had no cost of delay, where time wasn't important to me, and I just wanted to do an efficient way of doing things, I think sequencing, and I had perfect information, there's no reason you couldn't prove it was optimum to do one sequence instead of another. Okay? Now, we compete more in worlds with moving targets, and the targets move faster and faster. A long time ago, I was in the Navy on submarines, and the submarine I was on, this was during the Cold War, the Холодная война, and I had to look for another submarine in the middle of the ocean. The submarine could be going in any direction. We would know where it was at one point in time. Somebody saw a periscope, somebody heard a sound, somebody intercepted a radio signal. It could go in any direction. The area we would have to search was proportional to velocity squared and time squared. It was much easier to find a diesel submarine than a nuclear submarine, not because diesel submarines are noisy, but a nuclear submarine will add an annulus of area in 1 hour because of its speed that very rapidly exceeds your search rate with your platform. So you have to get to the datum very quickly. That's why we use things like helicopters and aircraft. They have terrible sensors, but you can get them to the location quickly, and you don't need great sensors if you get to the datum quickly. Now, in this case, uncertainty goes up with time squared because it's a 2-degree of freedom problem. Now, the location of that submarine is not a non-random variable. The submarine will be in different positions with different probabilities. So, in this case, it's 2 degrees of freedom. How many degrees of freedom do you have in your product requirement? Do any of you have 2 or less in your product requirement? We've got a huge problem estimating at long time horizons in markets that are moving, with technologies that are moving. I was working with a telecom company. They did a 6-month development program in a business that had traditionally taken 3 years to do the development. The project was extremely successful, even though it left some features behind. And the manager of the business went to me and said, "You got to talk to the team leader and find out what he did so that we can tell all of other project leaders to do it." I talked to the team leader. His name was John. I said, "John, why do you think you were so successful?" John, might be able to guess, was an engineer from his answer. John said, "We developed the product so fast that marketing didn't have time to change their mind." And I'm besides being an engineer and I'm an MBA, sometimes I sympathize with the marketing people. I said, John, I would have phrased it a different way. I would have said, you developed so fast that marketing didn't have to change their mind. Because the reality in your business is nobody can forecast at a 3-year time horizon in this space. Everybody can forecast at a 3-month time horizon. The single biggest thing you can do to improve the quality of requirements, and recognize that 80% of products fail because they're designing to the wrong requirements. It is not technical risk that is killing products. It's designing to the wrong requirements. And the biggest thing you can do to end up making the requirement problem go away is to shorten the transit time through the development process. And you do that by taking WIP out of the system. Extra WIP that causes a long transit time through development just exposes you to massive amount of requirements risk that is virtually impossible to manage. Okay, so let me clarify again what a random variable is. It's a relatively simple concept. Is if I said number of beans in the jar, if it was a non-random variable, that line in the center, that maximum likelihood number, might be the number of beans in the jar. There are 2,323. It can only take a single value. It's a variable that takes a single value. Okay. A random variable is a variable that takes different values, and there is a probability associated with each one of those values. It takes values associated with a probability function. Okay? And so we're always looking at the probability functions of our random variables. Now, how do we normally deal with this problem of randomness in our process? We have a lot of traditional remedies. We say, well, if only people plan harder, they can get out of it. Maybe we should just make low variability choices and things. Don't tell. Six Sigma, for example, was about telling people don't do things that have any risk. And there's a fundamental problem with some of these ideas, like when we use the approach of doing the low risk things, what happens is, yes, we shrink the negative tail of the distribution, but we shrink the positive tail of the distribution at the same time. Is that when we want to innovate, we have to do things that have uncertainty associated with them. If we strongly suggest to people they should avoid things that have uncertainty associated with it, it will drive out the innovation in a process. So that's not a good way to deal with the problem of risk in innovation, to say don't do risky things. Sometimes we try to mask the variability by having people undercommit on performance, pad their schedules, pad their budgets. That's also a very weak strategy, because if you look at something like that, if I build margin into the schedule, what I'm doing is actually I'm converting a small probability, I'm converting a probability of being late into a certainty of being late. I'm losing all of these early delivery options when I end up padding a schedule to say it will be, just to be safe, we're going to be done in 2018. That isn't the best economic choice. But buffers tend to be very hard to justify when you look at it economically. And then the other classic approach is going to be to use robustness as a way of dealing with the problem. We build a lot of inertia into what we do. So let's take a look at a different way of looking at it. Random variables will make us money, but they make us money because they get processed through what is known as a payoff function. And the payoff function is what can cause something, a variability to either create economic damage or to do economic good. And option pricing theory is probably the clearest way of seeing how that works. And that's what I want to jump into right now and just show you the way we would look at it from a financial perspective. So this is option pricing theory. Robert Merton, Myron Scholes won the Nobel Prize in Economics for option pricing theory back in the 90s. First time people had accurately quantified the value of a stock option. So how do you figure out what a stock option is worth? I've got 3 graphs up here. This first graph is the probability function. That is, what is the expected price of the stock at a point in the future? When the option expires, what is the probability that the stock will be at each one of many price levels? And just for those of you not familiar with options, an option is associated with a strike price. So if I sell you an option to buy Apple stock for $120 a share, what will happen is if the stock is below $120 a share when the option expires, 120 is the strike price, then you're not going to exercise the option because you can buy it on the market for cheaper than 120. If it's higher than 120, you'll exercise the option. Every dollar it's above 120, it puts another dollar in your pocket. So this upper left graph is the probability of the price being at a certain level. The upper right graph is what we call the payoff function. That tells you how many dollars you make associated with each one of these price levels. So anything below the strike price, you throw away the option. You always lose the same amount of money if it's below the strike price. If it's above the strike price, then you make more money, $1 for every dollar it's above. And this is what is known as an asymmetric payoff. And when you calculate the economic value of an option, you're doing what is called an economic expectation. And it's just like any other statistical expectation. You multiply a probability function by the function you're calculating the expectation of. We're trying to calculate the expectation of making money on the option. And so I multiply these price values by this payoff, and I get a curve that looks like this. And this is telling me how much of the option's value is coming from each of the possible price levels. If I take that total area below the 0 axis and above, the net area is the value of the option there. That's how we figure out the value of an option. Now, the interesting question one would ask is, what will happen to the value of a stock option if you increase the variability in the stock price? So when you increase the variability, you spread the tails on that probability function. When the tail spreads into the low payoff area, it doesn't change anything. You always lose the same amount of money. When the tail spreads deeper into the high payoff region, you make more and more money. And on this next slide, what I've done is I've drawn the graph with 2 different levels of variability. One is with a high standard deviation, the other with a low. And what you can see is on the left side of the chart, there's no difference in the area there. On the right side of the chart, there's a big change in the area. Now, the interesting thing is if you go to a lot of lean manufacturing practitioners, a lot of lean people will say it is always desirable to reduce the variability in a process. You see a lot of people say, oh, we need to put SPC charts on our software effort, and we need to reduce the variation in the process that we have. We need to get better and better at estimating and stuff because it's good to have accurate estimates and things. Well, you know, the interesting thing is that if a lean manufacturing person went to an economist and told the economist, we have learned that minimizing variability always maximizes economic outcomes, the economist would laugh in their face. They would say, you obviously understand nothing about variability and economics. You've got some great slogans, but they just bear no resemblance to economic reality. Is that there are certain conditions under which variability will, minimizing variability will make you money. There's other conditions where it doesn't make you money at all. And the important thing, and I want to be clear, the message I am giving you is not, oh, your mistake was you wanted to make variability go away. I want you to celebrate variability. No, celebrate variability is as stupid as minimizing variability. It is only when variability hits an asymmetric payoff function that you really end up making money. And let me give you sort of an example of an asymmetric payoff function that all of you would probably be familiar with from the software development literature. You all have probably heard of the lean startup approach, right? So lean startup, you define an MVP and you end up saying, yeah, I'm not really sure whether this thing is going to work or not. And then you test the MVP, and if it doesn't work, you pivot. And if it does work, you continue, you persevere and things like that. Well, what actually is lean startup doing to the economics? There was a tail of possible outcomes associated with that MVP. What lean startup has done, it has said, the bad outcomes, the negative tail, I need to dampen that negative tail. I need to minimize the damage done by the negative tail. I need to maximize the payoff of the positive tail on that distribution. And in fact, lean startup is a very interesting application of the ideas of anti-fragility in the product development space. Now, the question then becomes, how might we create these asymmetric payoff functions? And my argument would actually be that we have mistakenly been chasing after the process, the prospect of minimizing variability when we should be focusing our attention on creating payoff functions that allow variability to make money for us, that shut down bad paths, that amplify good paths. And I think there are reasonable ways to do that. The payoff asymmetries in product development are created with feedback loops. It's all about feedback loops. And the feedback loops is all about, as Alistair was talking about with his elephant carpaccio, it's all about small batches. You buy information in small batches, you exploit that information. That's what allows you to amplify good outcomes. What we're trying to do on one side of this curve, we're trying to amplify and exploit the good outcomes. On the other side of it, what we're trying to do is we're trying to dampen the bad outcomes in the process. Now, I like to use a little toy problem sometimes to illustrate the importance of buying information in small batches and creating feedback in processes. So I say, I'll let you buy a lottery ticket. Pick a 3-digit number. And if you pick the correct 3-digit number, I'll pay off $3,000, but I'm going to charge you $1 per digit. Now, if you buy those 3 numbers in one large batch, you pay $3 to get 3 numbers. That would be a break-even game, right? Poland is full of good mathematicians. This is not anything very difficult. So it's a break-even game if I pay $3 for one chance of 1,000 of winning 3,000. Now, what would happen if I changed the game and said, I'll still charge you $3 to buy a 3-digit number, but I'm going to charge you $1 to buy the first digit and then I will give you feedback as to whether you picked the correct first digit, and then you can choose whether you want to buy the second digit, and then I'll give you feedback, and you can decide whether you want to buy the third digit. The economics of that second game with feedback is radically different because there's a 100% chance I'm going to buy the first digit. There's only a 10% chance I'll buy the second digit. There's a 1% chance I'm going to buy the third digit. And now, when you say, well, and this gives me an average of $1.89 payout per game as opposed to 0 per game. And the question is, where did that extra money come from? And somebody trained in finance would say the difference, because it's still a $3,000 prize, there's still one chance out of 1,000 of winning it, and it's still $3 to play the game. What has changed in the second game is I have created embedded options in the game. I've created shutdown options after the first digit and after the second digit. It is the shutdown options in this case that is creating the added economic value. And so when you construct development programs that have you go marching all the way to the edge of the cliff, following the entire program all the way to the end, I think that is a huge economic mistake. You ought to be just the way lean startup structures shutdown options at the MVPs and things like that. You need to structure options to alter the emphasis on different features as you get more information in the process. And it's a different way of sort of viewing product development. What I explain to some executives, I say, the way you're approaching the world is as if product development is a horse race. And you try to pick which horses are most likely to win the race, and you place your money, and then you watch and you see what happens with the horses. I said, the correct way to think of product development is a horse race where you can move your money after the horses have started running. And you can take money off a horse that is falling further and further behind and add money to a horse that's looking more and more like it's going to win. And that's a totally different mentality than the waterfall model saying we're going to front end load all our decisions. You are guaranteed you will not be able to front load decisions if you are going to continuously be making decisions based on new information that arrives during the development process. I tend to view the new information we get from intermediate feedback as just a gift from the universe. And you can either exploit that information to make more money, or you can end up ignoring that you received that information. So for me, creating asymmetries, it's about buying information in small batches, creating shutdown options, truncating bad outcomes, amplifying good outcomes. I think this ability to exploit these asymmetries comes from creating a particular type of development process. Now, you could sort of guess that I'm not big on the traditional notion that conformance is the best way to do business, and fortunately, that's I'm pretty aligned with Agile in that respect. I tend to view that our traditional view that goodness was hitting the budget, hitting the schedule, hitting the performance target, is we're being given these constant opportunities to make decisions about the economic payload of our project. And if each time I'm presented with a decision, I make the correct economic choice, then when I get to the end of the program, I will have more economic benefit, more gross margin being generated from that product for the company than if I had stuck with the original plan. And for me, my test of whether the development program was run properly is I can look back at the end of the program and I can say, everything that we added to this project along the way is better than the worst thing we ended up leaving behind. Is, you basically got a truck you're driving to the marketplace. You've got the ability to put additional stuff on it. You've got the ability to throw stuff out and things like that. You want to make sure that the payload you bring to the end of the development program is the maximum payload that you had the opportunity to take to the marketplace. Okay? And that's my view of the world. There's lots of the things we do with Lean and Agile and stuff like that are aligned with that. We work in small batches. We have sprints where we can readjust at the end of a sprint and things like that. I think we still worry an awful lot more about estimating than trying to get good estimates than I would really suggest doing. I think in the Agile world, you do not make enough of a distinction between being able to estimate the bulk properties of a large quantity of stories and being able to estimate the individual properties of a single story. And if you can, in fact, estimate bulk properties of a lot of items together, that is what you need to manage projects. I was talking with a guy who worked at Cessna. I said, how do you estimate how much work it takes to do an aircraft? He says, we count how many engineering drawings there are in the aircraft, and we have a parametric estimate of how many hours per engineering drawing it takes. We calculate the total. This is 83,000 engineering hours. Therefore, if we have an engineering team of this size, it will take this amount of time to do. And I said, well, how could that be? So assembly drawings take much more time than detailed drawing is. Could you really just use an average parametric number for all the drawings? And the answer is, yeah, you may think it's not going to work, but it actually works quite well because the mix of assembly drawings to detailed drawings stays about the same from plane to plane. There's no the demographics of drawings does not change dramatically on our product. We can just use the average value very well to do our estimating. Okay, so that's what I wanted to talk about. There's probably a couple of intended takeaways. I think a fundamental belief that I'm dealing with a stochastic problem changes the way you manage product development. I think the waterfall model is just a disaster when dealing with stochastic development, and I think the world is getting more and more stochastic. Moving targets require very different approaches than predictable targets. You do a lot of course correction in flight. Risk aversion, buffers, and robustness are not as good a way of solving the problem as feedback loops. Accelerated feedback loops are the most economical way to deal with the problem of variability. Anti-fragility is a really interesting and useful idea. It comes from asymmetric payoffs. We can engineer payoff functions to create those sort of asymmetries. We should favor good economic choices over conformance to plan. My definition of a good choice is one that maximizes the economic payload of a project. We need to create the ability to quickly shift our priorities based on new information. I wish I had $1 for every development organization that complained to me that we shift priorities too often in our organization. If priority shifting is not intrinsically bad, if you're shifting from a bad choice to a good choice and things like that, is that if you create an organization that can't shift priorities in a world where customer preferences are changing and technologies are changing, I will guarantee you have a dysfunctional development organization. We need to accelerate decision cycles, and that's kind of an interesting. I'm glibly tossing that out. the way you get accelerated decisions, you do all the stuff of putting the authority and the information down where you want to get the decisions made. But there's a hugely important other dimension, is that if you haven't decentralized control before, you have to develop business judgment in those people you are giving the authority to make decisions, because they will not have made some of those decisions before. And there's a huge risk that they'll make a decision, it will blow up, and then you will revert back to centralized control. Okay, capacity to make risky decisions safely depends on creating good business judgment. Small batches, low whip capacity margin enable fast feedback. Now, you've probably, you know some of the books. This is the way we classify ski slopes in the United States. That intermediate, and expert. Principles of Product Development Flow is a hard read. You know, Eric Ries of Lean Startup said, not for the faint of heart. But it's not hard read because it's got a lot of fluff in it. I chose to put a lot of substance in it. Okay, so that's what I wanted to cover here, and I've got 10 minutes to take questions. I've opened a couple of boxes that I haven't completely closed, so I've got 10 minutes to take some questions.
Hi there. I thought that was very interesting what you were talking about with anti-fragility. I understand the math, but could you give me some actual examples of contexts or situations that are really anti-fragile?
Yeah, I mean, I can give you, maybe examples in product development of creating significantly asymmetric payoff functions, and because those are the ones that higher variability benefits. So you might look at the pharmaceutical industry when you're trying new drugs and things like that. In the pharmaceutical industry, you do not study a molecule that has been around for the last 40 years and studied by every biochemistry department in the world. What you do is you pick up a brand new molecule that somebody ended up dragging back on the bottom of their boot from the jungle or something like that, because it's only that really new, novel molecule, sometimes these engineered proteins, that has the potential to have a performance tail that will get into the range of a blockbuster drug. So they are always betting on these very high-risk molecules. The way they manage risk is they will take a portfolio of 200 leads with the belief that only one of them is going to end up succeeding, turning into a blockbuster drug. So all the advice they would get from business schools telling them, increase your success rate by betting on stuff that has higher certainty, is completely off the mark, because they want to bet on stuff that has the widest range of possible outcomes, because those are the things that produce the winners. When Boeing was developing the Boeing 777, they had a number of materials that they were looking at using for the plane, because the plane had a very aggressive weight target. They had things like aluminum lithium alloys, they had things like composite materials. Now, they could have used standard aircraft aluminum alloys that had been used for the last 40 years, very low risk, very low variability. But Boeing said, look, some of these new technologies have the potential to have significantly lower weight than aluminum. If I spend $50,000 checking it out and it works, I'm going to save hundreds of $millions on the cost of the plane. And so they were looking at a lot of their choices not to stay away from potentially risky materials and approaches, but to say, whenever I had this sort of extreme upside of a large weight impact for that particular material, then it was worth the investment because of the asymmetry and the payoff. I don't know if that helps at all. Okay.
I have a question about the lottery example that you used.
Yeah.
Don't you think that it was just slightly oversimplified? shouldn't be more like that for checking the first digit you actually have to pay like $2 or $1.50. So if you check all of them, you will actually pay more, because I think this is with the Agile, you do in small iterations. Of course, you will get feedback faster, but every step, because it's so Agile, has some overhead.
Yeah, and I mean, you could sort of see on this example that you could raise the cost of some of the intermediate purchases of information. You know, let's say there was an intrinsically higher cost to buying information in 3 small batches instead of buying it in 1 large batch and things. And often we run into that world. We say, system test, high fidelity, it covers everything. We shouldn't be doing a lot of little tiny tests. But the interesting thing in this case, you can see the economics of this game is $1.89 is the payoff. And you could raise the cost of buying information in those 3 steps by up to a total of $1.89 before the game would stop making money. And I think it is more realistic to say there are charges associated with buying information in small batches. For purposes of a group discussion, I like to keep the model simple and obvious and things like that. But you can see they're interesting. And the other really interesting enhancement to this is, which is more resemblance to what we do in product development, is why don't you give somebody the option of increasing the size of their bet after they have bought the first digit? You know, placing a bet on the first digit, but then if the probabilities start rising, increasing the amount of money they're placing on the bet. And that, when you work through the math on that, that starts looking really attractive when you start getting to the point where you don't have 1 chance of 1,000, but 1 out of 100 or 1 out of 10 of winning. Pulling some of the resources out of your back pocket to increase your bet is a pretty smart thing to do. And that's what venture capitalists do, right? Venture capitalists give you a bunch of venture capital. If you start succeeding, they throw larger bags of money at you. So you see a lot of this behavior, for example, in the financial world of venture capital without using the terminology of anti-fragility and asymmetric payoffs. Okay, good question. All right, any?
Hi. There's a in financial markets. There's if you're a trader, there's all kind of tricks and things that you can do.
Yeah.
Maybe where you become the source of the variation, and the investments you make change the way that other investors work.
Mm-hmm.
Are there equivalents in this kind of modeling with product development?
Yeah, so I mean it raises an interesting point of view, which is I was just talking about the issue of decentralized control and leadership at a conference last week, and about how the Marine Corps is the model I use for a military organization that understands how to do aligned decentralization, how to create initiative while still maintaining alignment. And one of the things you will see in Marine Corps doctrine is the statement that their view of uncertainty, which is that uncertainty does not intrinsically favor one side over the other. It favors the side that can function best in the presence of uncertainty. And Marine doctrine is not to survive in the presence of uncertainty. It is to thrive in the presence of uncertainty. And that's really code for creating this anti-fragile capability, is these payoff asymmetries. So what the Marines do is if they truly believe they can function better in the presence of variability than the people they're fighting with, they will crank up the variability. They will increase the velocity and the uncertainty on the battlefield because they know they are better prepared to deal with that, then the people they're fighting with will get further and further behind in the decision cycle, and then it ends up breaking into chaos when you can't keep up with the flow of the battle. So I think there is a real element of saying, if I can get really good at functioning in the presence of uncertainty, I can actually increase, the rate of change. And I probably have to say I've seen product developers do that, where the pace of their introduction of features sometimes is so much faster than some of their opponents that their opponents are always reacting to the last feature that they came out with, but never catching up. So I think there's an element of that in product development, or potential for it.
You mentioned decentralized decision making.
Yep.
What is the property of centralized decision making that makes it a problem? Is it the degradation of information, the speed of information transmission? Why not centralized?
Usually we find the pressure to decentralization because there are response time, there's bandwidth limitations at the top of the organization, and they cannot handle the velocity of decisions that have to be made in sort of a larger and more complex environment. You can demonstrate the centralized decision making is better for making a single decision. Usually the idea is that, the centralized decision maker has the power of omniscience and omnipotence, and therefore they know all things and they can make a better decision, and they control more power than anybody down at a low level in the organization. The problem is, in real life, you see very little of that omniscience and you see very little of that omnipotence. So usually what we worry about is being able to push control down to a low level in the organization where people can exercise initiative, but then to put in place mechanisms on certain issues to maintain the alignment. And I'll give you an interesting little example of this. I'll give you a real life example. Boeing was developing the Boeing 777. They had a performance guarantee on the plane. They would pay the excess weight of every plane United bought for the entire flying life of the plane. The plane was overweight. They said, what can we do about this? And they developed a decision rule that said, any engineer can remove weight for $300 a pound. If you can do a design change or material substitution and remove a pound of weight for less than $300, you don't need anybody's approval. So they had 5,000 engineers on that program making these weight decisions with no adult supervision. And when I used to be a consultant at McKinsey, our standard answer to that problem would be to say, the weight of the plane is a critical economic success factor. You need to have the most important person worrying about the most important parameters and things. So the program manager would have to make all the weight decisions, which would result in a 50-year development program. What Boeing did is the program manager used their perspective of system-level knowledge to calculate the $300 decision rule. That was a system-level optimum number. If you had just told 5,000 engineers to locally organize and remove weight and things like that, it would have been an utter disaster. But Boeing carefully recognized that we need to have the program manager control the logic of the decision, which allows us to flow the actual decision down to the lowest level in the organization. I think it's very naive to think that the centralized decision maker has no advantages on issues and things like that. It's just usually how do we get the very large number of small decisions that we need to get made effectively? We just can't run them up through high levels of the organization in most cases. Okay?
Thank you very much. Well, we need to close the discussion. Hopefully, we'll continue during the afternoon or evening downstairs. Please.
Okay?
Donald, thank you.
So, one more word of Polish. Dziękuję.